So why are areas of convection relatively constant as seen by the dynamic warm pool? So let's look at the balances we would expect in the convective regions and in the drier subsiding regions. So net heating or net energy loss over the dry regions or everywhere is the outgoing long wave radiation epsilon times sigma T4, where epsilon is the emissivity, as you remember, sigma is the Stefan-Boltzmann constant, and T to the fourth is of course the temperature, emission temperature to the fourth, very nonlinear term. And over the convective regions you have diabatic heating happening, which is related to the relative humidity and the temperature this way, with the density of the air, latent heat of vaporization, condensation, and the exchange coefficient, wind speeds, saturation humidity times relative humidity, and all these nice terms, ideal gas constant for water vapor, etc. And if the convective region has to remain constant, that means basically the region of outgoing long wave radiation with dF net dSST, where the rate of loss of OLR has to approximately match the area of heating in terms of dQE dSST. So this is related to SST, as we know, and that's what we are looking for. So as SST is warm and atmosphere is able to pick up the moisture and create deep convection and atmospheric heating, column integrated heating, these two have to basically balance each other. So as long as you are increasing SST and increasing convective column integrated heating, there has to be also region that is increasing with or there is a increased cooling over other regions, so that the areas remain approximately the same. Okay, so this is done with a two box model. The schematic diagram of the simple box model containing a convective and a subsidence region. So here is warm SSTs, there is subsidence and colder SSTs. So somewhere there is the threshold temperature where the so you are starting with the control case where there is a certain threshold temperature where the column integrated heating goes from negative to positive. The top panel represents the current state of the climate, where it's assumed that the convective SST greater than TH and subsidence regions are in dynamic and thermodynamic balance. So you have a mean temperature that's determined by convection and rising motion and column heating happening here, and there is a outgoing long wave radiation balance, net cooling balance happening over here. So the two boxes are in equilibrium. This represents the two box models after a homogeneous increase in SST in both boxes. So you have increased the SST here, as you can see, probably increased the area as we see in observations, and you have as we know already that as SSTs increase, the threshold temperature at which the column integrated heating changes from negative to positive also increases. So you have TH plus delta TH there. So this bottom panel is then going to show the heating threshold SST increase, but the area of the convective region remains almost constant. So you're looking at DWP area, I apologize for that, and SSTs, and you can see that convective area change is minus 1% per 1.5 degree SST increase. Okay, so the change in area is much smaller than the area you increase in SST. So here SSTs are generally given a shape and a magnitude to drive the convection, and then there are cooling calculations are done here. Basically these equations are solved for this simple box model. So relative to the surface area of the tropics in the two box models, the area of the ocean warm pool increases much more significantly than the dynamic warm pool area. So the results confirm what is observed, but this is maybe not as convincing. The same calculations were also done with what is called an Aqua planet model, where the entire Earth's surface is homogeneous and it behaves like a water world with there are various ways of doing. It's either fully coupled so that the ocean has circulation and everything, or it's just assumed like a slab with some heat flux that is taking heat out of the tropics to the poles, so that you maintain some equilibrium circulation that is realistic in terms of the equator to pole temperature gradients and the associated circulation in the atmosphere in terms of the Walker cell, the Hadley cell, and the ITCZs, and so on. And the sea surface temperature forcings are prescribed this way. So in this model, the Aqua planet is forced by observed or some distribution of sea surface temperatures, and you can see that it's not just the warmest SSTs that are increased, but also the gradients are almost maintained to be the same, and then the resulting circulation changes are looked at. So you see that you get strong vertical shears associated with increased sea surface temperatures at the edges of the warm pool. So if you think of the warmest region of the ocean as warm pool is over here, you can see that the vertical shears are not happening on the equator but away from the equator several degrees. So the convection is happening, as you can see here, on the equator, and the vertical velocity in pressure coordinate increases as SST forcing is increased, but the subsidence also increases on the other side, and you get also this mid-latitude storm track kind of behavior with a small vertical velocity that gets positive, but again you have subsiding regions on the other side. So the area of subsidence is much larger than the area of heating and upward vertical motion and the higher tropospheric temperatures. So obviously the deep convection keeps producing colder and colder temperatures at 250 hectopascal, as we know, and the surprisingly tropics end up having the coldest temperatures, which is also true in the real world, because deep convection, cold cloud top temperatures produce the coldest sea surface temperatures. So that explains how increased area of the oceanic warm pool doesn't necessarily increase in the dynamic warm pool, and the convection area doesn't increase that much. This is showing size of the dynamic warm pool relative to the surface area of the planet in the simple two-box model. So I should have shown that before, maybe. Anyway, and in the zonally symmetric Aqua planet, where you have the same SST distribution along all longitudes. Changes in total precipitation in blue line, magnitude of average vertical velocity within the convective region in the red line, wind shear at the edge of the convective region in the orange line. So these convections here, what else, are plotted relative to the present. Okay, so you can see that the dynamic warm pool is here, decreasing by a few percent only, whereas relative parameter change is shown here in terms of the forcings or the different responses. So here is the change in precipitation in blue, which is this line, looks almost black. Much larger increase in the precipitation, in vertical velocity, and change in wind shear. Obviously, if there is strong wind shear going to be associated with the expanding warm pool and the associated convection changes, one has to also worry about what that may mean for cyclones, for example, because tropics are the cyclogenesis regions, and we know that cyclones get suppressed, or they tend not to grow when there is very strong shear, because the energetic top of the cyclone tends to get sheared off and it doesn't grow. So that also has to be kept in mind as a response to the okay, so this is the box model and this is the dynamic model here, and the results are almost the same in the sense of a relatively small change in the dynamic worm pool when the SST worm pool increases. Okay, we will look at the longer term changes maybe in the next podcast, or maybe I should wrap it up here. So this is showing that such changes have been seen over long term as well. This is from the last glacial maximum where the entire globe was colder, so the entire threshold temperature and relative SST changes are shifted, but you can see that the negative and positive heating areas almost balance. So the idea of convective threshold decreasing doesn't change the relation between oceanic worm pool and the dynamic worm pool, and that's the same in the mid-Holocene period, and this is from the pre-industrial period. So over all the periods where SSTs have changed substantially and the worm pools have changed substantially, the relations between the oceanic worm pool change, the dynamic worm pool change, and the threshold temperature change all remain consistent in that the oceanic worm pool increase is not an indication of a corresponding increase in dynamic worm pool. So we have to then explain how the circulation change is happening while keeping the dynamic worm pool the same. Basically, you intensify the vertical and meridional circulations, and of course Walker cells as well. Walker cells as in Pacific, Indian and Atlantic Oceans, and subsidence and cooling is also increased over the subsidence regions, so you manage to hold the dynamic worm pool to be almost the same. So that's kind of the interesting result. We will look at circulation change in the next podcast to kind of close the arguments on why increase in oceanic worm pool doesn't bring corresponding dynamic worm pool increases, and convection in the atmosphere remains relatively constant. Okay?